we have waited a few minutes, and hopefully Dr. Carter will join us soon, but we can start the course. And today we have, will be only me. We are going to talk about atmospheric processes, air pollution meteorology, which is that section of meteorology that deals with air pollution problems. We will discuss air pollutants and their emissions, and we will start the discussion on air pollution modeling. So we have 4 lessons of 45 minutes. This is an introduction to air pollution modeling. So I expect that you don't have much knowledge of air pollution modeling issues. So I will start from the very basic at the beginning. Also, I want to tell you that I've been working on air pollution and air pollution modeling for 50 years. So I have an enormous amount of material. I could talk for a month. So during this course, I will have often to make decision about what to show, what not to show, skipping section, jumping from one section to another. I have a lot of material. Generally, I make this decision by myself or with some input from you. So don't hesitate to tell me if there are sections or topics that are of particular interest and I can dedicate more time. Otherwise, I'll have to make a decision and cut through all my material to be sure that we stay on time. Everything I show you will be available to you. Typically, at the end of each day, I will send you the PowerPoint, the PDF, whatever I've shown during the day and more, because as I told you, I have much more than I need. So at the end of the day, you will receive everything. So let's just start with some quick questions. If you can briefly tell me why you're here and what are your expectations and hopes for this course. Paula, maybe we can start from you.
My name is Maria Paula. I'm currently working for ERA, that is the Environmental Resource Authority in Malta. I make part of the team of air quality and noise, and I currently work with emission inventories focused on public electricity and waste sectors. And we already started the process to, because with the new air quality plant and the air quality guidelines, we want to introduce a bit of modeling because we are quite new on that topic. So we would like to get more into modeling and work as well with the data we get from the monitoring locations, because that's more related to ambient. So yes, that's all.
Very good, thank you. Mirfat, why are you here and what do you hope to achieve?
Hello, my name is Mirfat. I am from Saudi Arabia, Jeddah. I like the climate. I want to know about the modeling, also about air pollution modeling. I think this is good for my job because I teach in Jeddah University. That's all for me.
Very good, very good. Thanks again for attending. My name is Paolo. I've been working on air pollution and air pollution modeling for 50 years in Europe, in Kuwait, in England, in California, and now I moved a few months ago to Nevada, to a new beautiful city, a new beautiful area in Reno, Nevada. And if any of you happens to visit northern Nevada, let me know, and I will take you with my wife to the best Italian restaurant in town. I am the president of Envirocomp Consulting, a consulting company. I am also the president of the Envirocomp Institute, a non-profit research organization. And I am the director and founder of the Air Pollution Scientific Initiative, APSI. We will talk about APSI often in these 3 days. Okay, so as I told you before, we have today, I will be alone talking about meteorology, air pollution, and modeling. Tomorrow we'll have a great lesson by top scientists, Professor Musiopoulos, Professor Van Grisven, and Dr. Friedman. These are, again, people like me who have spent a lifetime on air pollution problems, and they will give specific seminar. And then I will have the last one on air pollution modeling. And finally, the third day, it will be me and another top scientist, Dr. Jacques Musafir, talking about air pollution around buildings, very sophisticated simulation. So I think you're very lucky because it's not just me, but there are other people, so other accents, other topics. We will try to keep you awake. I know courses are tough, especially if you are not face-to-face, but remain concentrated and you will learn a lot, I promise. Okay. Let's start with day one then. As I told you, I have a large amount of teaching material, so don't hesitate by voice or by emails to let me know what are your expectations, your priorities, because I can zigzag through my material to try to please your needs and follow your suggestions. The course is flexible. I will avoid complex math because it's an introduction. So there will be some math, but I will try to minimize complex maths. We will talk about local and regional air pollution, no global issues. This is very clear in the description of my course, air pollution at local and regional scale. There will be some intentional repetition because I think it helps. Some important topics will be sort of repeated sometimes, and there will be some jumping, as I told you, between PowerPoint presentation and PDF. I want to start by telling you about APSI because I've done a lot of work on APSI, and this is a gift that my generation wants to leave to you, the new generation. I've created a free, absolutely free repository of air pollution knowledge. So there is a lot of air pollution information on the internet, on Wikipedia, there are courses, you can find a lot of stuff. But I believe that what we have done with APSI is unique and will help you a lot in the future, completely free. The most important, and please visit apsi.tech and familiarize with all this material. It will be very useful to you. There are many important things here, but the most important is the matrix. We have created a matrix of more than 200 topics and subtopics. introductory, emissions, modeling, monitoring, air pollution engineering, and other topics. Also, we have initiatives, local studies, books, lecture sets, my courses. So there is an enormous amount of material here, which is well organized by topic. And for each topic or subtopic, there are guides and notes at a basic, intermediate, and advanced level. For example, for modeling, if you look at any topic, modeling of adverse effects, health risk assessment guide. You click on the guide and you have some information on this topic. Sometimes it's just brief with a pointer to a site. In this case, a AIHA risk assessment tools. In some other cases, you have, for example, again, modeling atmospheric transformation aerosol guide. Here we have a guide, a reading guide with an entire book of a chapter 9 by Dr. Seigneur, who allowed me to use his chapters in APSI, and you have an entire chapter here in PDF on atmospheric particles. So as you can see, there is a lot that you can find in on the web, but in APSI, everything is organized by topics. So you will be able to find a lot of useful material. Also is multilingual. We have automatic translation capabilities in all languages. So hopefully this is a free resource that will assist you in the future. After all this introduction, 15 minutes, let's start with the first main topic, which is atmospheric issues. We are dealing with air pollution, so we are dealing with chemical releases in the atmosphere. So I'm opening a new PowerPoint, and the topics of this section is emissions, atmospheric transport, diffusion, and deposition. That's what happened to air pollution when it's injected into the atmosphere. Air pollution is transported by the wind, diffused by turbulence, and eventually, fortunately, deposited on the ground. Deposition is the way the atmosphere cleans itself. Eventually, most pollutants do not accumulate in the atmosphere, but are deposited on the ground. Also, there are chemical reactions, very important. And all these issues need a proper management. So we have all the government all over the world that have established laws, regulations, agencies, procedures, guidelines, a lot of bureaucratic, sometimes very efficient, sometimes not very efficient, laws and regulation to deal with air pollution. There is also a criminal aspect. Many air pollution cases end up in court for litigation, for criminals activities, for people suing the industry or suing the government. And in particular, that's most of my work these days. I'm very much involved in litigation. So I'm often asked to do air pollution modeling, not just for science, but for clients involved in litigation, industries, individuals, class action, government, and so on. In all this discussion, it's very important to note that the role of computer model is essential. Is essential. You cannot deal with air pollution without having without using computers, both for data analysis, which is very important, analysis of data, visualization of data, statistics, graphs, trends, but especially for computer simulation modeling. Computer simulation modeling is the technique that we use to simulate all these things. We simulate emission, transport, diffusion, deposition, chemistry. Everything can be simulated by computers. So let's start from the beginning, the releases in the atmosphere. There are two types of releases, anthropogenic or man-made, due to industrial activities, urban activities, transportation, and natural, for example, volcanoes or dust storms. Chemical releases can be planned, like the normal, regular industrial emissions that you see from stacks. Those are planned. The emissions are relatively constant, and we know how much they inject into the atmosphere. Or can be unplanned, like maintenance activities, startups, or accidental releases. Incidentally, what I do most these days in my work is accidental releases. So I've done a little bit of everything, but recently I'm asked often to deal with accidental releases, which of course are more difficult to simulate because for planned release, we generally know how much is emitted, but for accidental releases is a challenge. And then we have emission of sort of traditional called criteria pollutant. These are the first pollutants that we started to investigate in the 60s and the 70s. These were like SO2, sulfur dioxide, CO, carbon monoxide, ozone. These are the criteria pollutant. They are this nickname criteria is often used. But then there are other pollutants that we discover their importance later, like for example benzene and many air toxics that we really started to study later, maybe in the 80s or in the 90s. And then another way to characterize the releases is primary, chemicals that are directly emitted in the atmosphere by sources. For example, carbon monoxide, CO, every time you drive a normal gasoline car, you emit carbon monoxide. And secondary chemical, these are chemicals that are not emitted by anybody. They are created in the atmosphere due to chemical reaction. For example, a typical example is ozone. Ozone is a big problem, still a big problem in urban environments, in cities. And we cannot point the finger at any emission of ozone. Ozone is not emitted. Ozone is created by chemical reaction of pollutants that are emitted by industry and transportation. And finally, to characterize the different releases, those that have a short lifetime, most pollutants, SO2, carbon monoxide, ozone, have a very short, benzene, have a very short lifetime, fortunately. They disappear from the atmosphere. They are deposited on the ground or they are chemically transformed into other chemicals. And those that have a long lifetime, like the greenhouse gases, CO2, carbon dioxide, and methane. So these are all the different ways to characterize our emission of pollutants in the atmosphere. Okay, so we talked for about 20 minutes now. Any comments so far? You can hear me well with my microphone?
Yes, it's good.
Very good, very good. So I will continue until 6:45 my time. To summarize, well, to visualize many of the things that I've said before, let me show you a few images. Natural emissions, volcanoes, forest fires, anthropogenic emission, man-made, automobiles, industries, and then adverse health effect due to the inhalation, human inhalation of these chemicals. At the beginning, until let's say in the previous mostly in the 19th century, industry was the major cause of air pollution. And then starting from the middle of the 20th century, automobiles have become a major cause. Perhaps the most important, transportation is the most important problem today, especially in the developing countries. Industrial emissions generally are limited in space in the industrial area, but transportation emission, cars, motorcycles, trucks are everywhere. And so often this is the main challenge we face, especially with the enormous development of transportation, of private transportation and public transportation, and the emission of cars and trucks, especially diesel. Diesel, as we will see, is particularly dangerous in terms of cancer effects. And the results, we can see the results everywhere in the world, especially in urban areas. These are a few images of a haze, this gray fog, the haze that is caused by air pollution, mostly from transportation and combustion in general. There's another image. I think this is New York. I think the previous one was Shanghai, but I'm not sure. Again, this is a typical, this is not the traditional industrial pollution of the 1950s in London. This is a new type of pollution, as we will discuss. I think this is Seattle, perhaps. Again, you can see this brownish area in the city up to a certain elevation. And this is like a cap over the city that is keeping all the pollutants trapped inside this layer. Okay, so why do we care about air pollution? Well, we care about air pollution because there are adverse effects. And the most important adverse effect, traditionally, the one that started all our concerns about air pollution, is the health effects on human. You can find some sources saying that there are 2.4 million people that are killed by air pollution every year. You have to be very careful about these claims. It's very difficult to analyze the death of people and to blame air pollution because it's a difficult statistical analysis. It can be done, but it's not that easy and the uncertainties are enormous. However, I want to show you both sides of the issues. Here there are some people claiming a very scaring number, and I wrote a section on risk and mortality here that is available on the web. I try to put things in perspective. I try to understand exactly what the situation is. Every time we talked about millions of people dying for air pollution, this type of risk have been calculated with animal experiment on animals and then translated to human. These are not real calculation. These are not autopsy of corpse of people who died that tell you, oh yeah, he died because air pollution in the lungs. These are statistical studies made on animals and then translated to humans. So the uncertainty is very high. There is a very famous study by Harvard. There is a very famous study, a Harvard report on cancer prevention that estimated that only 2% of people dying of cancer were associated with environmental pollution. So there are several studies that I encourage you to read if you want to know more about it. But anytime we talk about statistical risk, the uncertainty plus minus is enormous. In fact, the EPA, the United States Environmental Protection Agency, stated very clearly the true value of the risk is unknown and may be as low as zero. So, just a warning to check different opinion and not to believe only one side when people talk about air pollution. In particular, I want to show you a 4-minute video which I found fascinating. Perhaps you've seen it before, but it is a video showing human evolution in the last 200 years in terms of wealth, GDP, gross national product, lifeline, and different sections of the world. I'm showing you this video to reflect on how difficult it is to attribute to air pollution certain number of deaths, because the lifetime of our lives has been increasing enormously. In the last 200 years, we live much longer, from 40 to 80 in the average. And so to try to say that we could have lived 82 instead of 80 without air pollution, some people make this statement, but I want to warn you that it has a lot of uncertainties. So let's watch these 4-minute videos together, and then perhaps I'll ask you for some comments. Okay, so I hope you understand my point that the change in lifetime duration that we have experienced makes it very difficult to calculate the effect of air pollution on health. Very good. So let's continue for another 5 minutes, unless there are comments or questions. So let's start the section of atmospheric transport, diffusion, and depositions. Pollutants are carried by the wind from point A to point B. They are diffused by atmospheric turbulence, which is the vertical and horizontal fluctuations in the atmosphere. And they are deposited at the ground by dry and wet processes. Dry process is just the pollution touching the ground, and a fraction of the pollution touching the ground is trapped at ground level. And wet deposition is due to rain, snow, and any precipitation cleaning up the atmosphere and taking the pollution down to the ground with precipitation. A simple image to represent what I just said is here. We have industrial emissions, we have automobile emissions, we have the wind blowing from left to right, so the plume is going this direction, and then there is turbulence, so the plume is expanding, and then some chemicals are touching a tree, and so they are trapped inside the tree, and it rains. So these are all the phenomena that characterize transport, diffusion, and deposition, and these phenomena are dominated by meteorology. Meteorological factors are essential in affecting the impact of air pollution. Chemical reaction, very important because they create what we call is the urban smog, which is generated by chemical reaction creating ozone. As I told you, ozone is a typical chemical that represents urban smog. And ozone is a secondary pollutant created by chemical reactions in the atmosphere. So we call this a photochemical smog because, as we will see soon, ozone is created by photochemical reactions in the atmosphere. And let me give you just a simple visualization of what happened in an urban environment. This is very simple. I'm going to show something more complex later during the course. But basically, what happened in the urban environment is that in the morning, there are anthropogenic, man-made emission of nitrogen oxide and organic gases, reactive organic gases like hydrocarbons. So these are emissions for people driving to work, industrial emissions, so automobiles, industry, combustion. All these emissions create NO, nitrogen oxide, and ROG, reactive organic gases, practically hydrocarbons. The organic gases then react to become free radicals. Free radicals are molecules that are very reactive. very reactive. They tend immediately to create new reactions. So the original nitrogen oxide reacts with the free radicals and create NO2. Once we have NO2 in the atmosphere, with solar radiation, NO2 is split into NO plus O. O is a single atom of oxygen, extremely reactive and unstable. O will react with O2, oxygen in the atmosphere, and will create O3, ozone. Eventually, ozone will be destroyed by NO and recreating NO2. So this is basically what we know about urban photochemistry, simplified enormously. And the difficulty was to understand the reaction, the formation of NO2. We knew these reactions for a long time, but the challenge was to understand why we had so much NO2 in the atmosphere. And only by studying hydrocarbons and free radicals reaction, we were able to understand this process. NO original and O emission that are transformed into NO2. Once we have NO2 in the atmosphere, everything is starting to operate. So chemical reaction, the principle is the creation of the urban smog. And in the second lesson, after 15 minutes break, we will talk about other important chemical reactions that are the formation of secondary particles. So it's 6:45 now. I can take a few questions if you have some or comments. Otherwise, we'll have a 15-minute break.
I don't have any comments so far. So
Very good, very good. And I'll see you in 15 minutes. Bye. Very good. So let's start the second lesson. We were talking about chemical reaction, and the two main effects of chemical reaction in the atmosphere are the creation of the urban smog, which is typically characterized by ozone, by the presence of ozone, and also the other important effect of chemistry is the creation of secondary particulate matter. Fine particulate matter, there are 2.5 micron or less. We will talk more about particulate matter, but let me anticipate to you that chemical reaction create the transformation of gases, some gases, into small fine particles. SO2, sulfur dioxide, can be transformed into sulfates, small particles. Nitrogen oxides, NOx, can be transformed into nitrates, small particle. And volatile organic carbons, typically hydrocarbons, can be transformed into organic particles. And these secondary particles are one of the reasons we have acidic deposition. The plumes are emitted as SO2 and NOx. They travel for even 100 kilometers or 200. They are transformed into sulfate and nitrates. And these sulfates and nitrate create acidic deposition, acid rain that may damage forest. So these are the two main activities of chemical reactions: urban smog and secondary particles. Let's talk more about particles, just to give you an idea of what they are. Let's start with a typical average human hair. A typical average human hair is 60 micron. A micron is 1/millionth of a meter. So 60 micron is a human hair. And when we talk about PM10, particulate matter of 10 microns or less, this is the typical size in comparison with the human hair. And when we talk about PM2.5, fine particles, we are talking about 2.5 microns, which is represented here in comparison with a human hair. So they're very difficult to see, these particles. And this plot here is very useful. Is a logarithmic scale, so be careful. 0.1, 1, 10, 100. This is the particle radius in micron, and these are various types of particle. From secondary particle that we discussed before, the gas to particle sulfates and nitrates, bacteria, virus, dust, sea salt, drops, raindrops. So these are all the the enormous variation in size of what you can find in the atmosphere, from very small cluster of molecules up to raindrops. So there are 6 order of magnitude difference from the two extreme. And what are the effect of particles? One effect, we already discussed it before. It was acidic deposition. Another effect is particle invisibility. Fine particles in the atmosphere create a decrease in visibility, visual range. So we are very concerned about fine particles, PM2.5, near areas that are a tourist area. Like, for example, in the United States, the national parks, the Grand Canyon, the mountain area, the lakes, everywhere where people should enjoy a visual range long enough to see the environment, the mountains, the snow, the green, the forest. Fine particles are impairing, are ruining sometimes this visibility. These are 3 examples, and these are not pictures. These are images created by computer simulation. In other words, we change the light in the pixel. We do a computer simulation of visual range. We change the light of the pixel to account for the concentration of PM2.5. It is a computer simulation, and but it represents reality. If there are low concentration of PM2.5, you can see the mountains. If there are high concentration of PM2.5, you see this haze covering a lot of the visual range. So this is another chapter in air pollution modeling. It's called visibility modeling, which we will briefly talk about this during the course. Particularly important is diesel particulate matter, because it's PM 2.5. They're very fine particle, and they are mostly made of elemental carbon. We call it soot. Diesel are emitted mostly by heavy-duty trucks, but also by diesel car, construction equipment, and others. Diesel machines are very important for our life. All construction is done with today still with diesel equipment. And only recently we have discovered, I think this was done in July 2005. This was a big surprise about 20 years ago, when for the first time in California, the California Resources Board did a study of health effects of particles. And they were able to prove, let's say prove is always a big word in science, but they were able to show that based on our current knowledge, diesel particles were the dominant factor for estimating potential cancer risk in California. At least outdoor. Indoor, there are other cancer risks, in particular, environmental tobacco smoke, which is secondhand cigarette smoke. I hope you don't smoke, and I hope you don't spend time near smokers, because it is quite dangerous. And indoor smoke from cigarettes is today is well known as a cause of cancer, comparable and even higher, apparently, than the outdoor toxic pollutants, which are dominated by diesel particle. So nowhere is safe. Indoor, there are indoor air pollutants. Outdoor, there are outdoor air pollutants. So my suggestion always is to minimize your exposure to pollution indoor and outdoor. Okay, new topic. So if there is any question or comment, this may be the right time to let me know. Otherwise, I'm going to tell you a few things about management. I'm not very involved in management. My work as a modeler has always been research and development, development of new models, and recently modeling application to accidental releases. But there are many people who do air pollution modeling for air pollution management. So they work for government agencies or government department. So there is a big sector of the administration in any country dedicated to the management of air pollution. How do we manage air pollution? Well, we have so-called routine management at local level, local agencies at the city level or county level or state level. These are agencies and managers and government people that work to achieve predefined air quality goals in order to protect human health and the environment. This is the basic management done at local level. And then there is the emergency management, when something happened that is unexpected. And we talked about preparedness and response. This is difficult. Emergency management is difficult because in air pollution studies, if you have an accident, in less than an hour, the plume has moved to the community. If you do your calculation, with a wind speed of a few meters per second, in 1 hour, the plume has already traveled several kilometers. So there is sometimes very little that you can do during accident. Other types of environmental accident, for example, in water or in groundwater, you have more time to react. But in the atmosphere, the motion of the atmosphere is relatively fast. So it's very difficult to do emergency response. Of course, you have to try to be as prepared as possible. So emergency preparedness is always possible, but the response in real time is quite challenging. And then there are the large-scale issues, like issue that goes beyond the local level. For example, in the United States, there is pollution coming from one state and impacting another state, which is 100 kilometers away. Especially in the Northeast, there are many states like close to each other, very small states. There is transboundary pollution from the United States to Canada and vice versa. Also in Europe, there are areas where there are small states like, for example, Holland, Belgium, and Luxembourg, where pollution from one state can easily move to another in an hour or two. So there is management at the local level, management at the national level, and management at the European or United Nations level. And of course, there are global issues, which we will not discuss in this course. Computer modeling is the key tool for all these issues. No matter how small or how big, no matter how large your problem is, computer modeling is the tool to understand air pollution and to simulate the impact of pollutants at different downwind distances. We should be relatively proud of ourselves, especially, I would say, in the West, Northern America and Europe, for the progress we have done with air pollution. Of course, there is still a lot of work to do, but if we look at the measurement of air pollution in the last 50 years, especially starting from the 1970s, when we started having the first North American and European laws to improve air quality. There is a period, I would say, from 1980 to 2010, where the progress has been quite strong. For example, SO2, sulfur dioxide, in the United States. We had a 76% decrease in the level of SO2 in the United States in this critical period. a major improvement. SO2 used to be the typical chemical that represents air pollution in the previous century. All the big episodes of London in the 1950s and in North America, pollution was basically SO2, burning fuel that contained sulfur. If you burn a fuel that contains sulfur, the sulfur will react with oxygen during the combustion, and sulfur dioxide will be created in the atmosphere. So so these show the progress in the United States, and similar progress has been achieved for SO2 in many other places, in Canada, in Italy, in Germany. SO2 has been really a success story. PM10, some progress in the United States. Still, we are mostly below the national standard, so we are not at zero, but we made some progress. NO2 is critical, as I told you, for creating ozone. And again, some 48% decrease in the national average during this period. So again, some success. Carbon monoxide, enormous success, mostly because of the catalytic converters in our automobiles. The national standard used to be exceeded in many places in the United States in 1980, and now we are very well below the national standard because of this enormous progress, mostly on automobiles, reducing emissions of carbon monoxide from automobiles. In fact, people who commit suicide don't use automobiles anymore. Many people used to lock themselves in the garage, start the car, and kill themselves with carbon monoxide emitted by the automobile. Now it's difficult, to use this method to commit suicide because car emissions are very much lower in terms of carbon monoxide. Lead, that is another big success story from 1980 to our century, because everybody was using leaded gasoline for car, gasoline with lead. And then eventually we were able to redesign our cars with the help of catalytic converters, and this has reduced enormously the emissions of lead from our automobiles. Ozone, some improvement, still improving today, 2023, but in the critical period of these 30 years, other chemicals have been reduced a lot, but ozone is still mostly above the national standards in many US cities, and is a problem all over the world, ozone and particulate matter. It is an urban problem all over the world, and many developing countries that used to have a relatively clean air now in their cities, because mostly of the traffic and transportation, they have enormous problem with air pollution, with ozone, secondary particle. We can see if you travel to Lagos, Nigeria, if you travel to Mexico City, if you travel to Shanghai, Beijing, it's air quality has improved in the West, but has in the last 50 years, but it has decreased. Air pollution has increased in developing countries. PM 2.5, some progress. We started measuring PM 2.5 in the United States only in this century. So we don't have any idea of past value. They were probably quite high. So I think we have made some decent progress on PM 2.5 too. In many places in the world, PM 2.5 is not measured. They only measure PM 10. They only measure PM 10. But PM 2.5 is even more important, because PM 2.5 is more dangerous for human health and for acidic deposition and for visibility. So they are both quite important, PM 10 and PM 2.5. So if you are in charge one day of designing monitoring station for your area, remember, don't skip PM 2.5. Do both PM 10 and PM 2.5. And again, to put things into historical perspective, I'll show you a few pictures. This is Los Angeles in the 1950s. I lived in Los Angeles for almost 10 years in the 1980s, and it was really, really bad. You didn't notice when you are at the office, because air conditioning is cleaning the air. So you work at the office in the morning, and it's fine. And then you go out for lunch, or you leave your office at 5, and you notice an enormous pollution, photochemical smog, burning your eyes. And this was typical, first in Los Angeles and then all over the world. We will talk more about the Los Angeles smog. Let's continue this initial introduction. As I told you before, air quality modeling is the key. Is the only way to establish a mathematical relationship between emissions and concentrations. So when we inhale air pollution, we are inhaling concentrations of chemicals. These chemicals are emitted by sources. Air quality modeling tells you all the mechanism, all the physical and chemical mechanism between emission and concentration impact. Many people say we don't need modeling, we can just do monitoring. Well, they are wrong. We need both. We need both. Why monitoring is not enough? Well, can you monitor everywhere? No, you can only monitor in specific points. Can you monitor all the time? No, you can only monitor at certain times. Can you monitor in the past? No, you can only monitor now in the present. Can you monitor in the future? Of course not. You can only monitor at the present time. So modeling is important because modeling can do everything. Modeling can simulate in the past, in the present, in the future, and you can simulate all emissions in all points. Even more important, if you measure a chemical, do you know where it's coming from? Of course not. This chemical may come 20% from source 1, 30% from source 2, and so on. Therefore, modeling will tell you not only the concentration caused by a source, but the fraction of each source. Modeling will tell you that 20% of what you measure came from the power plant, 30% from the refinery, and 40% from the automobiles. So modeling has enormous capabilities for management. It tells you everything. And of course, modeling needs to be verified, calibrated, evaluated with measurements. So we need both. Measurements are extremely important because measurements tell you where the model is wrong. But eventually, if you want to do real management of your air quality problems in your area, you need modeling. Monitoring is not enough. Models incorporate the best deterministic statistical science, the best relationship, mathematical relationship between cause, the emissions, and effects, the concentration. A simple figure to show the basic modeling, air modeling methodology. We have emissions, we have meteorology. These are the inputs. And the air model is giving you the output concentrations. Very simple. Two main inputs, emission and meteorology, and one main output, concentration, in every point at every time. So now let's talk about the input. I need the two basic inputs to run my air model. Emission and meteorology. Let's talk about emission. What is the relationship between emission rates and concentrations? Well, in some cases is almost linear. What does it mean, linear? Linear means that if you double your emission, concentration will approximately double. If you cut them in half, concentration will approximately be half. So if the relationship between emission rate and concentration is linear, do we really need models? Some people may say, no, we don't need models, because if the relationship is linear and our region is polluted and I want to increase my air quality by 30%, I just reduce the emission by 30%. It's linear. So I don't need to struggle with model simulation. This is theoretically true, but is not really true in practice, because you don't want to reduce the emissions homogeneously 30% to achieve an improvement of 30%. You don't want to do that. You want to reduce the emission in an optimal way. You want to reduce the emission that are easy to reduce, that are cheaper to reduce. So you don't want to do across the board reduction. That is a simple solution, but is not the most cost effective. So even when there is a linear relationship between emission rate and concentration, it's still important to go through modeling to be sure you understand what are the emissions that are dominant that you should focus on, and what are the emissions that are easy to reduce in comparison with others that are not. So you have to do management. You have to do intelligent management use model. And then there is the case where the relationship between emission rates and concentration is nonlinear. In that case, you have no choice. You really have to go through modeling. So what does it mean nonlinear? Nonlinear means, well, I reduce my emission by 20% and the concentration reduce only by 5% or by 0%. Or in very extreme cases, I reduce the emission by 20% and the concentration increase. Can you believe that? Is that possible? Yes, it is possible. In the complex nonlinear chemistry of the urban smog, we may have scenarios in which you have this absurd situation that you spend millions to reduce certain emissions, and you end up with an increase of concentrations, the opposite of what you want. To show you an example of this, I will show you a very simple urban ozone model, the most simple model that you can do for ozone. And we will talk more about this later in the course, but just follow me. Is relatively simple. We have hydrocarbons, volatile organic compounds, emissions along X in your city. We are dealing with a city here. Let's imagine this is Los Angeles. So on the X, we have the emission of VOC, hydrocarbons, reactive hydrocarbons. On the vertical, we have emission of NOx, nitrogen oxide. And all these curves here are ozone level. So 0.4, 0.34, 0.24, 0.08. And let's assume that Los Angeles is in this situation. The ratio of VOC versus NOx of the emission is 8:1. So we are in this straight line because we know the ratio in Los Angeles of the emission of VOC versus NOx. So what is the highest concentration value that you measure in Los Angeles over the year? Let's assume that it is 0.3. So 0.3 here, 8:1 here. The Los Angeles situation is here. This is the dot of your city. If I want to improve the ozone, I can decrease the emission of VOC, and so this will move in this direction from 0.3 to 0.24, good. Or I can reduce the emission of NOx, and I will move from 0.30 to 0.24, good. Or I can reduce both, and I will move along this line from 0.30 to 0.24. So you have three different strategies. Let's see if I can put three different strategies. Strategy number one, strategy number two, okay, doesn't let me add the strategy number two and strategy number three, which may have different costs, but they all end up in improving your ozone level from 0.30 to 0.24. You can do it this way, or this way. That's fine. But what happens if your city is here? If your city is here, 4-1. Let's say that Jeddah, for example, Jeddah in Saudi Arabia, we measure 0.30 of ozone maximum over the year, and we believe that the ratio NOx to VOC to NOx is 4-1. Well, look, if I only decrease the NOx emissions, I moved from 0.30 to 0.32. So I spend millions of dollars reducing the NOx emission, but in this city, we are in this scenario, and we actually increase the ozone concentration. The best strategy in this city is to do the opposite, to do this strategy here. Decrease only VOC, and then we'll have the best optimal improvement in ozone. So another example is another city. Let's say Boston. Let's say this city here. Let's say Boston in Massachusetts. You can see I'm not going to draw any more line because I'm sure you got the concept. If I reduce only the VOC in this city, nothing happened. I will continue to have the same level of ozone. I have to decrease the NOx because we are in the NOx limited area. So depending on where you are, your strategy for improving the ozone concentration in your city can be very challenging. How do you do this? With models. Only with models. You need to have very complex urban photochemical models that are able to simulate the photochemical reaction in your city. And you need to know the emissions, you need to know the meteorology, you need to run these models, and believe me, a mistake may cost billions of dollars, in not choosing the best strategy for improving the air quality in your region. So this is a typical example of non-linearity in which models are absolutely indispensable.
May I ask something, Paolo?
Certainly, go ahead.
If you come back to the graph,
Say it again.
can you come back to the graph you were showing us before?
You want these graphs?
Yes, just for the case of Boston, the example you gave us,
Yeah.
which one would be the ratio of VOC and NOx in that example?
I forgot to tell you. Thank you for the question. It will be about, this is 15 to 1, and this probably is 20, 25 to 1. Just an example.
Okay, okay. Okay.
Yeah. Yeah. For this city here, the ratio was 4 to 1. We started with this one ratio 8 to 1, this
It
15 to
is.
1, and this is probably 25 to 1. Yeah.
Thank
Good. Thanks for the question. We have a couple of minutes, and we will restart here. Yeah, I think that I'm not going to start this with limited time, so this may be a good place to stop. We have a minute for a question if you want. Very good. Then I'll see you in 15 minutes. So let's continue here. So how do we do air pollution modeling for management purposes, not just research or application consulting, just for management? So if you work for an agency, for a government agencies, what can you do for management? There are two types of models that you may use: dispersion modeling and receptor-based or source apportionment models. In this course, we will talk mostly about dispersion modeling. But I want to be sure you know that there is another option, which sometimes is quite useful, which is based on data analysis. These are basically statistical model, receptor-based. We'll talk about that, and they don't require a full understanding of the atmospheric processes. They just require an analysis of measurements. Let me check one thing. Yeah, I have a horrible lights here that bothers me, but it will go away in a minute. Okay. Another way of categorize the model that are available is based on the model input that are required, the spatial scale.
Sorry, Paolo.
Yeah.
You are not sharing a screen.
Oh, thank you. Thank you. I knew there was something wrong. I forgot to share the screen. Thank you. Okay. Here we are. You see my screen?
Yes.
Very good. Thanks. Okay, so we were talking about dispersion modeling versus receptor modeling. I'll tell you more about it, but basically most of the course will focus on dispersion modeling. And then other ways of looking at model is based on their inputs, on their spatial scale, local, regional, continental, on the temporal scale, just a few hours or a few years, On the treatment of transport, there are Eulerian model and Lagrangian model. You may be already familiar with these two terminology, but we will discuss it later. On how the model treat various processes like chemistry, deposition, and on the complexity. Some models are relatively simple, others are extremely complex. So in choosing the model for your air quality management purpose, you will have to consider all these issues. And the choice depends on a combination of what is available data, your needs, and your budget. Sometimes, budget may be limited and you can only afford a certain simple model, or you may have a lot of a good budget and a good team to work with, and you can afford a more advanced technology. One of the guest speakers will talk about available models, so I'll go quickly on this. But basically, the best way to start is with the models recommended and developed by the US Environmental Protection Agency, EPA. They are free. They have been developed for decades. They are well tested. They are well documented. They can be directly downloaded from the EPA.gov Scrum from this website. You have dispersion modeling, you have photochemical modeling, you have receptor modeling, you have, for dispersion modeling, you have the preferred model, the alternative model. For the preferred model, you have AirMod, which is used all over the world. In other words, if you start with the EPA website, you have everything, and it's all free, all free. My modeling books are all free of charge online. I wrote the first comprehensive book on air pollution modeling in 1990. It's still valid, it's still used by many people. I also did more recently a comprehensive air quality modeling book series. You find them here. For example, the third volume, you can click and you can download the entire book or only some chapters. For example, all the chapters here are available for download. Actually, sorry, they are available at APSI. At APSI, you have to go to APSI to download free all my books. Volume 3 here, it has all the chapters in the index, and you click on the index, for example, Gaussian plume models. Here we are, chapter 7b, you have the entire chapter. So again, through APSI, you can have a lot, all my courses, my books, and a lot of other information. All right, so this is a good start. EPA models and all the documentation that is available. Special modeling of emergencies. That's something that I do all the time these days. Is really my one of my specialties. And for emergency, I already told you, there is emergency preparedness, which is relatively easy. Emergency response. That is difficult because things are too quick in the atmosphere. And post-emergency evaluation, accident reconstruction. This is what I do often. A week after the accident or a year after the accident, I'm asked to do the accident reconstruction and to assess the responsibility, what happened, how much pollutants were emitted, where did they go, who was affected, whose fault is. So this is quite interesting. I like it because every case is unique. Let's talk about the three main dispersion models that people use: the plume modeling, the puff modeling, and the particle modeling. First of all, again, there are EPA models versus other models. For example, I use often the EPA models, but I also had developed my own models. So sometimes I use both. Sorry, I need a candy. Otherwise, just a minute. Generally, I lose my voice on the third day of my courses, but this one, I started losing my voice on the first day, so I will have to be careful. All right, so there are EPA model and other models developed by people, by scientists at different universities, for example, around the world. There are simple models, like, for example, the Gaussian plume model. We'll talk a lot about the Gaussian plume model. And there are puff model and there are particle model. For example, one of the model I developed that I'm quite happy about it is the Monte Carlo model. Let me show you an example of application of this particle model, which I did 15 years ago. I cannot show you my most recent project because they are confidential, but I can show you this one. Today, of course, we have better animation capability than 15 years ago, but again, I cannot show them to you. But I can show you this just to give you an idea of what a particle model is and how high resolution you can have with a particle model. And then we'll talk about other models later. This is an example of visualization of an accident. This was an ammonia release. Actually, no, this was a chlorine release in Louisiana near New Orleans. This is a chlorine production area, this blue area. And this is the Mississippi River, very close to the site. This is the release location here. And this is a 2-hour animation of the release simulated with a particle model. You see, I generate hundreds of particles at the location of the release, and I simulate their transport and diffusion downwind. I'm going to rewind now. So you see again, the particle has different colors. Red is the highest concentration. Blue is the lowest concentration. And as you can see in this particular case, we were able to prove that, yes, we had the release. It was a big release, but fortunately, I stopped the animation now. Fortunately, the plume went along the industrial area. By the time the plume left the industrial area, the concentration were relatively low, the blue dots. So the impact was, unpleasant. There was some odor problem here, but it was not as bad as could have been if the wind direction was blowing directly from the release location to the area here, population area, or here. So fortunately, the release went this way. And we were able to prove it with a simulation modeling using particle. Practically, we simulated the gas of the chlorine with a set of tracer. These particles are tracing the pollution in the atmosphere. So this is an example of a particle model that I wanted to show you in order to show you how we can use very high resolution technology to simulate air pollution. Most of the time, we do not use this type of model, but if we need, we have tools that can give you this type of high resolution. These are other examples. A big fire here, black clouds simulated by a particle model. This is a simulation of an eruption, volcanic eruption. This is a picture of the eruption, and these are the simulation of the concentration created by the volcanic eruption at different level, from 2,000 feet to 35,000 feet. This is a simulation, again, of a radioactive release in Spain that actually moved to northern Italy. It was in 1998. So this, again, is a simulation using high resolution particle modeling. And finally, before we leave this presentation, I just want to point out that the future, what the future we expect to be in terms of modeling. And we have a prototype here. This is a presentation that we gave few years ago. in 2021, a couple of years ago, of a global modeling system for high resolution meteorological and air pollution forecast. We are still working on this. If you are interested in installing this prototype in your area, you should contact the main author here, Roberto Bianconi. I work with him on a daily basis, but he is the main developer of this system and the person that can install it in your computer at your area. And basically, this system is a global modeling system. You can choose a point on the Earth, any point. Can be Saudi Arabia, can be United States, can be Europe. You choose a point, and immediately the system will load available meteorological data and meteorological forecast for example, the next 3 days, 72 hours. So you have the meteorology now and the meteorology in the 3 days ahead. And then if you define an emission scenario, or if you have a suite of emission scenario, you can make a real-time simulation for the next 3 days of air pollution in your area, because you have the meteorology, you have the emission. So anywhere in the globe, you can start a simulation for 3 days in advance to see if you have an accident or a release, where will it go in the next 3 days? And is mostly automatic, eventually will be fully automatic. I'm not going to go through all the slides, but just to give you an idea that of the system to calculate the meteorology and the air pollution. There is a script that is available to start this simulation. And there are a few examples. For example, here we choose a release in an area near the border between Italy and Switzerland. And then in a few minutes, we get the meteorology for the next 3 days. And then in 10, 20 minutes, we can run the air pollution simulation. And this is an example of what you can get very quickly in any point of the globe. You can get a grid. You can get the meteorology. For example, this is the temperature in this area. You can have again, the meteorology here. You can have wind speed and wind direction, wind speed, temperature, precipitation, wind direction. So in this particular point at the border between Italy and Switzerland that you have chosen, you can have all the meteorological variable for the next 3 days quickly available. And then you can run a plume. You can run a simulation for the next 3 days of where the plume will go, using your emission scenario or some predefined emission scenario here. And of course, we continue to develop this system to incorporate as much information as possible. And right now, it can be installed in your computer by contacting Roberto Bianconi. And you can do a lot of nice simulations with this automatically. So this is probably the way of the future for air pollution simulation forecast in real time. And perhaps we will add artificial intelligence features in the next few years. Sorry if I have to keep a candy in my mouth, but otherwise I will lose my voice. I hope you can hear me well in spite of the candy. Very good. We have another 20 minutes. So this presentation, I think, is over. And we can start talking about atmospheric processes. Here I'm borrowing a lesson from Dr. Frank Friedman, who is one of the guest speaker tomorrow. And I will go through some slides. This is the Earth atmosphere. The thickness is about 500 kilometers. But of course, the higher you go, the lower the density. So a large fraction of the atmosphere in terms of mass is concentrated near the Earth, but the entire atmosphere is about 500 kilometers. And this is an example of an example. This is a figure showing the variation of air pressure and air density with the altitude. Of course, the higher we go, the lower the pressure, the lower the density. 50% of the mass of the atmosphere is found in the lowest 5 kilometers. So the lowest 10% of the atmosphere has 50% of the mass. There are several main atmospheric layers. The troposphere is from ground up to 10 kilometers. The stratosphere is from 10 kilometers to 50, all approximately. The mesosphere is from 50 to about 90. And then there is the thermosphere above 90 kilometers. All these layers have different characteristics. The troposphere is where we have the clouds and most of the mass of the atmosphere. And in the troposphere, typically, the temperature decreases with height. We know that. If we take our car and we drive to the mountains, we know that the higher we go, the lower the temperature. So, and this is what this red curve shows. If we start at 15 degrees Celsius at the ground level, we go up and 10 kilometers above the ground in an airplane, we may have minus 60 degrees Celsius. If we go only 3 kilometers above the ground, we may have from 15 to minus 10. So these are the typical change of temperature in the troposphere with the elevation. In the stratosphere, on the contrary, the temperature increases with height because of the ozone formation. Ozone in the stratosphere is beneficial, is a natural chemical produced by natural reaction, protecting us from harmful ultraviolet radiation. So ozone in the atmosphere, in the stratosphere, is beneficial, but in the urban areas at ground level is a pollutant. So don't get confused between good ozone 30 kilometers above the ground and bad ozone 100 meters above the ground. Then there is the mesosphere after 50 kilometers, in which again the temperature is decreasing with height, and then the thermosphere, where the temperature is increasing with height. So these are the main levels. Of course, we live in the bottom part. All human activities are in the bottom part of the troposphere. So that's where we care to understand meteorological phenomena. And when we talk about air pollution meteorology, basically we talked about the lower level of the troposphere. That's where air pollution is affecting human activities and human health. The composition of the atmosphere is gases, water, clouds, and aerosol. Gases include water vapor, is a gas. Hydrometeors is water in liquid of solid phase. So clouds, haze, rain, snow, hail. And aerosol are particles, suspended particle, can be liquid or solid or the combination of both. They tend to be very small in size because if they are large, they will settle. Large aerosol will be affected by gravity and be deposited quickly to the ground. But small aerosol, PM10, PM2.5, will hang there. Eventually, yeah, they may be deposited eventually. But they may will remain suspended in the atmosphere for a long time. For dry air, the composition of the atmosphere is 78% nitrogen, 21% oxygen, 1% argon. Water vapor can be from 1 to 4%. 1% very dry climate, like the one I am experiencing here in Nevada. 4% very humid climate, like northern Italy or other places. And of course, there are trace gases listed here at percentages very, very low, less than 0.1%. if you want to read more about atmospheres, this is a very interesting pointer. Is the evolution of the atmosphere. Is a history over billions of years over the Earth, how the atmosphere was formed, and the evolution of atmosphere, oceans, and continents. Very interesting. History of the Earth, how we reached a situation where we have so much oxygen that has allowed the life that we know in the planet. And also an effort to discuss the history of atmospheres in other planets like Venus, Mars, try to see if we understand the history of the evolution there. So I'm not going to spend any time here, but if you are interested, this pointer is a good way to start reading about evolution of atmospheres in different planets. Quite interesting. This is a typical example of a picture showing the level of the tropopoles 10 kilometers above surface. The top of the clouds in this case represent the change from troposphere to lower stratosphere, about 10 kilometers above the ground. So sometimes we see this layer. There are several slides here on meteorology that I'm going to go through quickly. This is not a course in meteorology, but I'm sure that many of you are aware of weather maps, pressure charts that meteorologists use to understand the local situation and to do forecast of weather in the next few days. You probably noticed that weather forecast has improved enormously in the last decades, the last 2 decades, because of models, because of meteorological models. Now we have very reliable forecasts in many places of the world. Of course, once in a while, they are wrong, of course. But we are able to trace tornadoes, hurricanes. We are able to do reasonably good meteorological forecasts for a few days, and sometimes even for a couple of weeks sometimes. Long-term meteorological forecasts are more difficult. They are very important for agriculture, the long term, like 1 year. They are very important for agriculture, but they are quite difficult. But 1 week meteorological forecast is relatively good. For those who are interested, there is more information here about the sun, the auroras. They don't really affect air pollution. Again, discussion of atmospheres on solar system. I will skip this, but you will receive all these presentation. Just to mention, the basic Earth life cycle is plants producing oxygen and animals producing CO2. And CO2 is a nutrient for the plants. So there is this cycle between plants and animals, especially mammals and others. that in which O2 oxygen is created and consumed, and CO2 is created and consumed. This is the basic of life on Earth, this exchange. Human respiratory system, very important for toxicologists to understand the effect of air pollution in the human respiratory system. So I'm not a toxicologist, but I work with toxicologists all the time because I do my simulation of air pollution and they use my results to calculate the human impact. So in all my projects, there are toxicologists using my results to develop their own opinion. My work finishes when I give the concentration calculations. We need oxygen, O2, for our life. This is the best range for humans, 19-23% of oxygen. If we go below 19, there are problems. That's why the higher you go, the less oxygen you have. And for some people, this may be a problem, even at low altitudes. Let's see what we have here. More discussion on oxygen. I'm not going to elaborate, but if you're interested, there is more information here on oxygen for breathing. And finally, this is an example of a bad effect of oxygen. A good effect is that it is absolutely indispensable for life on Earth, but like many chemicals, it has positive and negative effect. One of the negative effect is corrosion, the creation of rust in for iron, and the damage that this produces. Very good. So we are 3 minutes away from our stop of the third lesson. When we restart, we will talk about a key issue of air pollution meteorology, which I mean all the meteorological parameters that are important for understanding air pollution. So air pollution meteorology is a sub-science of meteorology, just for air quality applications. So I'm going to open this, and I think we can stop here. We have 2 minutes for questions or comments, and then we will restart from this point. So any question or comments?
Yes, excuse me. I have a question about the ozone. Why it's become not good, lower?
Because ozone in our environment where we live, in our cities, is a very reactive compound, is oxidizing from a chemical point of view. It creates burning eyes for people. It may damage your lungs with high concentration. And I can open and see adverse effects of ozone. It can burn mouth, nose, and eyes, can cause coughing, nausea, vomiting, headaches. So it is clearly at high concentration. Ozone is a typical chemical that may produce adverse health effects. It also damages material. If I remember well, ozone can damage rubber, the rubber of the wheels of cars. It is something active. It's not like those chemicals like CO2, for example, that is practically inert. It's a very chemically active compound that may do damage to your health. So everything fine so far is more or less what you expected. Think about it. Let me know today or tomorrow if there are topics that you are particularly interested. As you can see, I have a lot of material and I need to make quick decision what to show and what to skip. Otherwise, we'll take 30 days instead of 3. So think about it and let me have your feedback by voice or by email. And we will continue in 15 minutes.
Okay.
Very good. Let's start the last lesson of the day. I think I share everything and my microphone should work. Let me know if it does not. Air pollution meteorology. These are very important topics. Again, I'm going to borrow some slides from Dr. Friedman on air pollution meteorology. The most important issues on air pollution meteorology are winds and inversions. There are many others, of course, but the wind and inversion is the top. Why? Well, wind, of course, is transporting pollution from point A, the emission, to point B, the area of impact. So wind and wind fluctuations play a very important role. You are familiar with wind fluctuation. You can see them all the time. Just look at the wind moving the leaves and the branches of a tree. Just look at an industrial area. Look at the air pollution, the black air pollution coming sometimes from sources. There is basically a transport from A to B, but also there is a dispersion, an opening of the plume like a cone. The plume opens up like in this image. The emitted plume opens up. Let's use a bigger shape. Where did it go? All right. Well, you can see this blue line is, I wanted to do it thicker, but with PowerPoint doesn't really work. So this black plume here is opening up like a cone. a cone in the vertical, see my hands, and the cone in the horizontal. And we will simulate this cone later with the Gaussian plume model. You will see. But there are many other factors. There are the clouds impact, there are precipitation, there is impact with the receptor, there is mixing, dilution. There are a lot of phenomena in the atmosphere that need to be accounted for. So the wind transport is taking the pollution from A to B. The meteorological variables are wind speed, wind direction, and pressure. And then there is dilution mixing, this opening of this cone that I discussed a minute ago, which is caused by turbulence. What is turbulence? Turbulence is described by eddies. And these are the eddies here, example. These circular motion, counterclockwise or clockwise, that can be small or large. And those eddies are the key factors in creating dilution and dispersion. Of course, the peak air concentration are reduced with distance from the source. The more the plume travel, the lower the concentration. Of course, because the cone is expanding the plume. So expansion of the plume means that the concentration inside the plume will be lower. The more you travel, look at my mouse, from here to here to here to here, the more you travel, the more the maximum concentration inside the plume declines. So the meteorological variable of interest are wind speed, temperature, of course, day and night is a big change, temperature inversion, we'll talk about that, and pressure system.
One question, Paolo.
Certainly.
Would be humidity as well important in the
Yes. Yes, exactly here we talked about chemical reaction for gases in the gas phase and chemical reaction in the aqueous phase. So chemical reaction depend on relative humidity, and they are quite different actually in presence of water vapor and clouds. For example, the formation of nitrate and sulfates is very depending upon relative humidity and chemical reactions. Let me close the window because I have some noise. That's my gardener cutting trees. So this is a summary of chemical reaction in the gas phase. Those are the reaction that creates ozone, ground level ozone. Just to remind you, we are not talking about the good ozone in the stratosphere. We are talking about bad ozone at ground level. And photochemical smoke. These are all gas phase reaction. And then there are other chemical reactions that are accelerated, are faster with the relative humidity, clouds, and presence of water, like the formation of nitrate and sulfates. And our model takes care of all these things. All these phenomena are taken care by the equation that we use to simulate chemistry in our models. So for the gas phase, the key meteorological variables are temperature and sunlight. Remember, photochemistry requires sunlight to operate. We will see that. And in the chemical reaction in the aqueous phase are affected by humidity, cloud coverage, and precipitation. Then there is atmospheric removal. I told you that's the way the atmosphere cleans itself, mostly with dry and wet deposition. And so one of the main meteorological parameters is precipitation. The more precipitation you have, the more the atmosphere is cleaned by the water. That's why after a big storm, the air quality is excellent because a lot of stuff has been removed from the air. For long train transport, like 200 kilometers, other meteorological parameters are all meteorological parameters are important, in particular, wind speed and wind direction. A small error, when you do long-range transport, a small error in wind direction, 5 degrees, will, over 1 or 2 days of transport, will take the plume tens of kilometers away from the actual point of the plume. The error can be enormous. That's why long-range transport is difficult. It's difficult because small errors in wind speed and especially wind direction may cause enormous errors in the location of the impact of the plume. I remember when we had the Chernobyl nuclear disaster, and we had in the 80s, 1986, if I remember well, and many modelers started simulating the cloud from Ukraine, Chernobyl, that the cloud went first north to the Scandinavian countries, Sweden, Norway, and then south all over Europe, and then all over the world. We measured a slight increase of radioactivity all over the world because of Chernobyl. And many scientists, including some of my friends, did simulation of the Chernobyl cloud. And it was tough. It was tough because after a day or two, the error in the location of the plume was very, very large, very large. So they ran the model, but they had to correct the model with measurements to be sure that the simulation was correct. This was a typical example that we need both. We need the model and we need the measurement. We need the model to simulate the plume, and we need the measurement to do sort of correction, validation, to adjust the simulation of the plume to match the evidence of the measurements. That's the best way to do modeling. So, wind direction. Wind direction is typically caused by pressure, difference in pressure. I don't know why my mouse is not working well today, but these are examples of plumes carried by the wind, and wind direction is the number one parameter that we need to evaluate correctly. because wind direction means that we can simulate where the plume is going and will affect only people in that cone of impact and not other people that may be in other areas. A typical cone of impact of a plume may be 20 degrees, so less or more or less. So only people in that cone of impact will be affected. Of course, other people will see the plume. They will not be inside the plume, but they will see the plume. So it is very important when you study accident to account for both people impacted by the plume in terms of inhalation and people impacted by a plume just because they see the plume. So it's a question of a fear that needs to be evaluated. For example, people may sue in the industry for health impact, but they can also sue the industry for fear and for decrease of property value after an accident. So litigation can be very complicated after accidental releases. One of the best way to visualize the meteorology in one area is the windrows. The windrows is practically the first step people do in terms of meteorological analysis most of the times. First step. You choose a period of interest, for example, 1 year. You collect all the hourly measurement of wind speed and direction in a station located in the area of concern for 1 year. And then you visualize them with the windrows. The windrows is telling the frequency of occurrence of winds from all directions. For example, look at this bar. This bar is the wind coming from southwest. The bar ends here, so is about 90 hours. Okay, so this windrows tells you that during the period of interest, that was probably here maybe a month or a week, they don't say, but that's a typical value. We have 90 hours of wind blowing from southeast. We have 80 hours of wind blowing from south-southeast. We have 75 hours blowing from south. We have 40 hours blowing from west, and so on. So it's a statistical summary of the wind's direction, but it tells you more. It tells you more. For example, let me open this. It tells you more. Let's use this one, which is even better. For example, this windrows tells you that during the period of interest, in your area of interest, the winds from southeast occurred 13% of the time. And the winds from west occurred 6% of the time. And the winds from southwest occurred 8% of the time. You see here is the circles are the percentage, and the length of this bar are the frequency for each wind direction. Just remember, this is not the direction the wind is going to, is the direction the wind is coming from. Very important. Many people confuse that at the beginning. So this is a useful summary. Is even more useful when you use color to represent the wind speed. For example, the green color here tells you that the winds from southeast blowing between 4 and 6 meters per second occurred 4% of the time. And the wind from northwest blowing greater than 40 meters per second, blue area, occurred 1% of the time. So any combination of wind speed and direction, you have the frequency. So this is very, very useful at the very beginning of your project. One of the first things to do, the wind roses. Using the data measured at meteorological station in your area. You may have one station, you may have 5. For each station, you do the wind rose for the period of interest. Your period of interest may be 3 months, 1 year, 5 years. Do the wind roses. And by the way, there is software available that does it for you. For example, my friend and colleagues at EnviroWare, I work with them on all my projects. They have a wind rose that they give for free. Very nice. Very nice. Is a is a wind rose that can give the traditional segment and can also give the isoplet representation, can give the dots, the color dots, or the histogram. You know, they have several features. Here are the color dots. They all give you the same information. A statistic summary for wind speed and wind direction. So get this software, which I think is free, and start using it. All right, pressure. I'm sure you are familiar with the basic concept of atmospheric pressure. We may have high pressure, you know, good weather, low pressure, maybe bad weather coming. High pressure means that the air is sinking because of divergence. And low pressure means that the air is rising at the ground level. And so sinking and rising air may create important phenomena, because sinking is associated with high pressure and causes temperature inversion that trap air pollution inside the our region. Let me show you what happened. This is typical, by the way, of Los Angeles area in California, that has a typical semi-permanent Pacific height, high pressure, so good weather. But good weather also means that good weather also means this. Good weather means that there is sinking air, and the sinking air is creating a temperature inversion. What is a temperature inversion? A temperature inversion is a layer where temperature in the troposphere is increasing with height instead of decreasing. And when this happens, this is like a cap. This is like a cap. For example, in Los Angeles, typically we may have from 300 to 400 meter, just average numbers, an inversion, and this inversion will keep all the pollutant trapped inside the city. And the city is in a big valley surrounded by mountains. And the wind is blowing from the ocean. So everything is trapped. Everything is trapped. The wind comes from the ocean. The mountains are around. The top, there is an inversion. All the pollutants remain there. And they cook with strong solar radiation, and bingo, you have ozone and photochemical smog. It's not a coincidence that the first time we noticed photochemical smog, ozone, was in Los Angeles. Los Angeles is the perfect design for creating ozone, for photochemical smog. Perfect scenario. In the 40s, they started having serious problem because of industrial emissions and traffic. And this geographical, meteorological, unique scenario. Then later in the 50s, the 60s, we had this type of pollution all over the world because of the automobiles, essentially. But the first time we saw it was in Los Angeles. The first serious episodes of photochemical air pollution in Los Angeles was in 1943 during World War II. Many people believe it was a gas attack from the Japanese because it was so unusual and so bad. So for a moment, there was fear of a military action against the city with poison gases. 1943. And then Los Angeles was affected by this pollution for decades. It was only in 1953, 10 years later, the first big episode that people started understanding the chemistry and the photochemistry of this episode. And one of the key factors is the inversion. High pressure, sinking air, creation of the temperature inversion very near to the ground, 300, 400 meters, 500 meters, typically in daytime. In daytime, we have the solar radiation that creates all the photochemical smog. So temperature inversion are very important in air pollution. And there are two types of temperature inversion. The subsidence inversion is what we have discussed a minute ago. That's the high pressure, sinking air subsidence inversion. Typical of summertime, typical of daytime, and that's the second type. The first type is the ground-based inversion, typical of nighttime and wintertime. And let me show you what happened. After sunset at nighttime, the ground, typically the surface of the earth, cools down quicker than the atmosphere. So the atmosphere remains relatively warm, and the ground level becomes cooler. So for a certain layer, let's say maybe 100, 200, 300 meters, for a certain layer above the ground, we have that the temperature is increasing with height and not decreasing. This is an inversion. And again, an inversion is not this scenario. Be careful. It's not the daytime scenario with the inversion blocking the pollutants below. This is a ground-based inversion. The pollutant here will be trapped, but from the ground up, and only during nighttime. Okay. And these are examples of what happened. This is a typical nighttime radiation inversion with cold air trapped in a valley. You see the fog, that's because it's an inversion. The fog is stuck there. This is another example of nighttime urban pollution trapped wintertime. I think this is Denver. I'm not sure. Or maybe Salt Lake in Utah. Yeah. Yeah, it's written here. Salt Lake in Utah. Denver is same thing. And you see the layer of fog and pollution that has been trapped during the nighttime. So again, there's another example. I already told you this thing, but there are new figures that will really show, in case you missed exactly what happened. High pressure, sinking air, creation of the inversion layer, temperature is decreasing with height, increasing with height, decreasing with height. Typical daytime situation in Los Angeles, pollution is trapped below the inversion. This is the subsidence inversion. The other one here and here was the ground-based nighttime inversion. Our model can simulate all these things because they are designed to simulate the physics of the atmosphere. Another example of Los Angeles. This is the ground level. This is the subsidence inversion. And this is all the pollution trapped inside the Los Angeles. The red is the temperature, the variation of the temperature with height. Decrease with height, increase with height, decrease with height. Okay, any question on this discussion of air pollution meteorology so far?
I have a question, Paolo, but not sure if you will explain in detail, maybe, but I'll ask. So in this case, how the plume will behave or spread along during inversion conditions?
The wind flow, you mean, I suppose. The wind flow will change from one city to another because is is affected by pressure. In the case of Los Angeles, the wind flow typically is from the ocean to inland. So in the case of Los Angeles, there is a relatively constant daytime flow from west, southwest into the city, and then into the valley. Let me show you. For example, if we have a map, Los Angeles, a map of Los Angeles. So this is Los Angeles. As you can see, the valley of Los Angeles is surrounded by mountains. So, and the wind is blowing from the ocean during the day. So there is a top inversion layer that keeps the pollutant attached to the ground. The wind is blowing from the ocean. So if you live in Santa Monica, Long Beach, Huntington Beach, you have typically clean air coming from the ocean. But then all this big highway, the traffic is enormous. All this white here highway, the traffic is enormous and will create a lot of pollution. So this pollution is carried by the wind toward Los Angeles, Pasadena, and then there are the mountains. So the wind will bend from going from southwest, they will bend going from west. And so the pollution go to Ontario, San Bernardino, Riverside, Beaumont, and it's not a surprise that the more pollution travel during the day, the worse it is, because pollutants react and they have chemical reactions. So the pollution gets worse and worse and worse. 11 a.m., Los Angeles, peak, Pasadena peak at noon, San Bernardino peak maybe at 2, 3 o'clock. So we have different peaks of ozone at different time of the day, at different location. This is the typical, especially summertime, daytime Los Angeles scenario. Used to be extremely bad in the 50s and the 60s. I work in Los Angeles in the 80s. I used to live in Pasadena. And when I left the office at noontime for lunch, it was the eyes were burning. Now it's better. Still, there is room for improvement, but it's much better. So the 50s were a disaster. The 80s were still bad. And the worst was downwind. Each city is different, however. Los Angeles is the perfect design for photochemical smog, but now we have photochemical smog everywhere, even at high latitude, even in the Scandinavian countries or in cold countries, we may have Mexico City, for example, is like Los Angeles 20, 30 years ago. Really bad. Beijing, very bad, very bad. So this photochemical smog has spread everywhere, but now we know how it works. So we know how to control it. The only problem is very expensive, extremely expensive. A major step ahead was the catalytic converters in the cars. We will talk about that. Okay. Okay. The next, we can initiate the next one. I don't know why my mouse today is having problem. I changed the battery, but okay. This set of PowerPoint slides is I will go quickly here because it's a history of air pollution, ambient air pollution. You can look at this on your own. It's not really related to modeling, but I just want to say a few words. Two definitions of air pollution. One is air pollution is when you have some damage to human health, to the environment, to buildings, to work of art. For example, in Venice, Italy, there is a lot of concern of pollution ruining the stones and the marbles and all the work of art. In other words, one definition of air pollution is something that creates some damage. Another definition of air pollution is any change of the normal composition of the atmosphere. Even if we don't think it's producing adverse effects, any change is air pollution. So you can use the one that you think is more appropriate for your work and your city. Let's go quickly here. One of the best ways historically to control air pollution is through legislation. In the United States, the turning point was the Clean Air Act of 1970. This was a federal legislation for the entire United States, because many legislation are only for states within the United States. The Clean Air Act was a federal and was imitated all over the world. So if you look at the legislation in Europe and many other countries, they all started imitating the Clean Air Act. The Clean Air Act imposed ambient air standards, concentration of pollutants that are not supposed to be exceeded. If they are exceeded, then a new set of regulations starts to improve the situation. This is daytime in Donora, Pennsylvania, 1948. This is a traditional SO2 and particulate air pollution. This was near an industrial area. Horrible episode, multi-day episode, 1948. Los Angeles in the 50s and the 60s, even in the 80s, was not pleasant. The National Ambient Air Quality Standard was a big turning point. Let me show you. National Ambient Air Quality Standard. Did I do wrong? These are the current National Ambient Air Quality Standard for the most important pollutant, the criteria pollutant, carbon monoxide, lead, NO2, ozone, PM 2.5, PM 10, and sulfur dioxide. They are for short period, like 1 hour, and for long period, like 1 year. And some are statistical standard. Statistical standard are a little difficult to explain, but for example, for NO2, the standard is the 98th percentile of 1 hour daily maximum concentration, average over 3 years. I know it's difficult to understand. You have to read it a few times and you will understand it. So these are called statistical standard. They are preferred because they are values that can be exceeded. we accept that this value can be exceeded, but only in a very small number of cases. Other standard not to be exceeded. So this is fixed, 0.15 micrograms per cubic meter for lead. But for NO2, 1 hour, we give a little bit of tolerance before we say, you have exceeded the standard, so you need to be punished. And then there are primary standard and secondary standard. Primary is human health, secondary is protection in general of the environment. For example, odor level that should not be exceeded are secondary standards. And of course, every state in the United States, the United States in theory is a union of independent states. So each state has its own standard, its own rule that go on top of the federal rules. So California in particular, California has an enormous number of state environmental rules. So people in California have to comply with federal rules and California rules. And then there are county rules. So it's quite complicated, the compliance with environmental laws in the United States. As I told you, these are the criteria, air pollutants, those that are the most important one, but there are many others like toxic air pollutants that are important. If an area in the United States is okay with air quality standard, we say that that area is in attainment. If the standards are exceeded, the area is non-attainment. And it's very important for an area, a state to be attainment, because there are many consequences in being non-attainment in terms, for example, of federal support, federal money given to the states. If you are non-attainment, you may not have as much federal help as other areas. Okay, 9:45. The lesson is finished. Tomorrow we will restart at this point. And we'll talk modeling. We'll talk a lot of modeling tomorrow, and we will have the guest lessons. So we have a 15 minutes of discussion, which I can use to go ahead, or I can use to answer your question or comments. Anything from you?
Not from my end.
Okay, so let's try to finish then this section so we can start tomorrow. What else can I tell you about in general about history of air pollution? Of course, all pollutants have a natural background. For example, nitrogen dioxide has a typical background in clean air of from 0.2 to 5 ppb. So whenever you do your air pollution studies, don't forget to include the background because it may be important. Whatever air pollution is added by anthropogenic activities goes on top of the background. And in terms of health effects, don't forget that concentration level are important. That's why we have the standards. That's why we have the standard to protect. The primary standard are designed to protect human health. But don't forget that the duration of exposure is also important. For example, carbon monoxide at the level of 5 ppm, sorry, at level of 600 ppm for 20 minutes may have no effects. And then after 1 hour, you have a headache. After 2 hours, you have vomit. And after 10 hours, you die. So a same level of carbon monoxide that has no symptoms for half an hour exposure create death for 10 hours exposure. So the standards are important, but remember that there are many, many factors that affect our interpretation of air pollution. I need another candy. Okay. Let's see if there is any other. Implementation. How do you implement regulation? Well, this is just an example. In California, we have at the national level, at the federal level, the Environmental Protection Agency. Then we have the California Air Resources Board. We have the EPA Region 9 covering California and other states. Then within California, we have the Air Quality Management District. For example, there is a big Air Quality Management District in the San Francisco Bay Area, and there is an even bigger Air Quality Management District in Los Angeles, South Coast, and there are others. The Los Angeles is historically the first Air Quality Management District, I believe, in the history of the world, certainly in the history of the United States, because it was the first area where we found an incredible, dangerous urban air pollution problem. Still today, the Los Angeles Management District is one of the best. They have the biggest budget. They do a lot of studies. They do research. They sponsor consulting. They are quite active. I've done some project for this district before. These are the region of the EPA, 10 region. The region 9 covering California, Nevada, and Arizona is the one that cover where I live. So there is a lot of bureaucracy, and is very expensive. So many people criticize the budget, the environmental budget in the United States. They have achieved a lot of results, but the costs have been incredibly high. If I were asked by a country, I don't know, a country, for example, by Saudi Arabia or by Colombia or to help design a air quality management system, I would certainly try to imitate the America system, but with a much better, I believe. Now that we know, a posteriori, now that we know certainly I would recommend something less bureaucratic and more cost effective. However, the results of the American and Canadian environmental protection system has been quite good historically. The success of all this activity, all this money that has been spent, billions of dollars for environmental activities, is shown in the graphs that I showed before. For example, for carbon monoxide, the improvement from 1980 to our century have been incredible. Mostly because I already told you, because of the catalytic converter. Car with catalytic converter reduce enormously the emission of carbon monoxide, NOx, and hydrocarbons. So the problem with the catalytic converter is easy to steal. We have a big problem in, especially in California, of people who go at nighttime. People park their car in the streets. They go under the car. They steal the catalytic converter. They resell it for $50. And to change it, you have to spend probably $2,000. So that's a big problem. If you want to know more about the catalytic converter, of course, there is a lot in the literature, but it's really really powerful for automobiles emissions. Yeah, you have a pointer here that discuss the catalytic converter in detail, I believe. For your curiosity, these are the counties in the United States that are non-attainment. So most of the United States, the air is relatively clean. The measured concentration are below the air quality standards. But in the Northeast and in California and even southern Arizona, we have some problem. We have still some problem. It's not as bad as 30 years ago, but we have still problems. Oops. Finally, in many areas, the regulator, the government agencies, have designed what they call an air quality index. It is a number to simplify communicating with the population. Instead of talking about ozone, carbon monoxide, SO2, nitrogen oxide, we combine all these chemicals into one index. We call it AQI. So there is a formula to combine it. The formula is designed to take into account the different effects of different chemicals. And so once you apply this formula, you obtain a number between 0 and 500. So 0 to 50 is color green, clean. 50 to 100, moderate air pollution, yellow. And red, 150 to 200, unhealthy. This is a way to communicate with the public with one simple number and one simple color. As a scientist, I don't like this simplification, but it is useful to communicate with the public. The newspapers like to put this color in the forecast of the next day. You buy the newspaper, or you check the web and you see the air pollution forecast in the following day. So you may decide how much you exercise. You may decide if you want to spend a lot of time outside tomorrow or you want to stay indoor. So it is a way of for the government, for the agency to communicate with the public in a simple, straightforward, colored way. Okay, so we are finished today. We will restart tomorrow from here. I'll go fast. I'll go very fast because tomorrow I want to talk about air pollution modeling. So again, let's review what we do tomorrow. Tomorrow we'll have the 3 guest speakers, and then I will start air pollution modeling 1 and 2 during my my lesson. So we are a little behind, but we'll do what we plan to do. Very good. Thank you again, and I'll see you tomorrow.
Thank you.
Thank you,
Bye-bye.
Papa. See you tomorrow.
See you tomorrow.
See you tomorrow.